Howdy, y'all. Welcome back to Multi Aviation. In this video, I'm going to be talking more about aviation weather. This is our part 4 series, and I'm going to be breaking this up into a few different videos. So in this videos, we're going to be talking about the atmosphere and heat imbalances. Now, if you're thinking, man, that sounds boring, you're right. So, this is just one of those things that you kind of need to learn along your way to truly being a master of learning aviation meteorology. There's a lot of boring topics that we have to learn about, but in the end, if you have the patience to get through these videos, you're gonna understand the more complex material later on when topics start getting a little bit more complex. So stick around so we can get to it. So I'm Dr. Andy Moltar. I'm an experienced flight instructor, a CFI IIMEI. I'm a former corporate pilot, and I'm a professor of aviation. And aviation weather is one of the classes that I've taught at my university. All right, so in this video, we're going to be talking about the Earth atmosphere, the energy balance, which includes solar radiation versus terrestrial radiation. And then in the next video, we'll talk about heat imbalances between the Earth's surface and the atmosphere. And then in the video after that, I'll be talking about heat imbalance with variations with latitude. And then in the next video after that, I'll be talking about seasons. And then our part 4 series will end by talking about the diurnal temperature variation. All right, so the Earth atmosphere and heat imbalances. So, weather is the atmosphere's response to unequal rates of radiational heating and cooling across the Earth's surface and the atmosphere. So, we have incoming solar radiation that heats the Earth's surface, and then terrestrial radiation from the ground causes the cooling. So, the heat from the surface escapes back out into space. There are imbalances in the rate of heating and cooling, which create temperature gradients, which we'll get into. And the atmospheric circulations and weather atmosphere's never-ending attempt. I'm sorry. So atmospheric circulations and weather are the atmosphere's never-ending attempt to redistribute this heat and achieve equilibrium. So basically, you have something that's hot, something that's cold, and they're trying to reach equilibrium to be the same temperature. And so, since that will never happen with the air, these energy transfer exchanges are going to happen, which lead to all of Earth's weather. So, the Earth atmosphere energy balance is the balance between the incoming solar radiation and the outgoing terrestrial radiation. So, some solar radiation is reflected back to space, but some solar radiation is absorbed. And I'll show you this in a picture here in a second. And then we also have the terrestrial radiation, which is much weaker than solar radiation. And when you really get into it, you're going to find out that it has a longer wavelength, so less energy. But it goes further. So an example, terrestrial radiation would be like rising heat from a hot road on a sunny day. I know in the news you hear about like greenhouse effect, and this is nothing political. There is greenhouse effect, and we do need the greenhouse effect to survive. And so retaining terrestrial radiation helps maintain the temperatures on the Earth. So without a greenhouse effect, the average temperature on the moon is negative 18 degrees Celsius, which is well below freezing, versus 15 degrees Celsius on the Earth. And so 15 degrees Celsius is equal to 59 degrees Fahrenheit. So it's, yeah. All right, so greenhouse warming is enhanced during nights with overcast skies. And I'll show you that a picture of that later. So here's a figure from the Aviation Weather Handbook. It's the Earth Atmosphere Energy Balance. And so it's just showing you, if you can see my cursor. In fact, I'll make it a, where is it? A laser pointer. So here you see the sun. This is just saying that it's like 100% of solar radiation. And so as that solar radiation is coming to Earth, 8% of it is going to be reflected by the air back into space. 17% of it is, so the solar radiation hits a cloud, and so 17% of that radiation is reflected by the cloud and goes back into space. 6% of it, the solar radiation hits the ground, and 6% of that radiation goes back out into space. 19% of the solar radiation gets absorbed by water vapor, dust, and ozone layer. And then 4% of that solar radiation gets absorbed by the clouds. So only about 46% of solar radiation actually gets absorbed by the ground. So that's our solar radiation. Now let's talk about our terrestrial radiation. So with our terrestrial radiation, here's our long wave radiation, where here's 15% of our terrestrial radiation, where 6% of that gets absorbed by the clouds, water vapor, carbon dioxide, and ozone. But in the remaining 9% gets, goes out into space. All right. So then we have 7% of that terrestrial radiation that is sensible heat transfer, and we'll talk about sensible heat later. And 24% of that is latent heat transfer, and we'll be talking about that in a little bit in the next video. All right, so 40% of the terrestrial radiation is emission by the water vapor, carbon dioxide, and the ozone, because remember, with the solar radiation, a lot of that gets absorbed by the water vapor, dust, and ozone. And then 20% of that radiation is emission by the clouds, and this all goes out in space. So we have 100% of solar radiation that comes to the Earth, and then we have to have 100% of terrestrial radiation that goes out into space. If it's not perfectly balanced, well, if it's more solar radiation, we would cook to death. If it was more terrestrial radiation, then we would freeze to death. So it's in perfect harmony. It's exactly what we need to survive on Earth. So as I was saying earlier, then we have the greenhouse effect. And so the greenhouse effect, if we have clear skies, here it is, it's 25 degrees Fahrenheit, and all that terrestrial radiation from the ground is just radiating out into space. But once we start having clouds, the clouds will actually help keep, trap some of that heat so it stays on Earth here. And so it actually, during the winter, if you're thinking like, man, it's cold, and then you start to see like clouds and overcast skies, you may be thinking, oh man, it's gloomy, it's going to be colder. Well, at night, those clouds actually help retain heat. And so you can see over here, we have like an overcast layer, and now it's 45 degrees Fahrenheit. And so with just the addition of these clouds, the temperature actually increases substantially. And so it helps trap some of that heat, so it's not that cold. All right, well, that's it for this video. In the next video, in part 4B, I'm going to be talking about heat imbalances. So make sure to subscribe, and so you can get notified when the next video comes out. And if you have any questions, leave it in the comment section. I'll be happy to answer them. All right, you take care. Bye.